Can you hear me okay? All right, thank you. Thanks, Mike. Thanks, Dimitri and Ingmar, for the great hospitality. I really had a great time talking to various faculty members and good interaction with them. So I know that Dimitri and Mike and Kumar are initiating this EPIC initiative, which has as pillars multi-phase, multi-physics, and multi-scale modeling. I spent my entire career looking at multi-phase flows and multi-scale modeling, things like that. And as a young researcher, this was many years ago, maybe 25 years ago, when I started out, I will claim that, well, I can make these predictions for fluidized beds at various scales. And people will ask me, how confident are you? Not all, but at least some people used to ask, how confident are you in these predictions? And I would say, yeah, I'm quite confident because I'm using fundamental laws of physics, momentum balance, mass balance, energy balance. I'm using experiments to validate my models. So there it is. It's pretty confident. I'm fairly confident. Of course, those days we did not have a good framework. Neither did the people who asked me that question, nor did I have a framework to really say how confident I was. But during the last 15 years, that has changed, especially in the nuclear industry, since they got rid of this nuclear testing because of the Comprehensive Test Ban Treaty. They started using modeling to prove that these weapons will work. These are not used, but you want to prove that it works. And how do you prove that? Using computational techniques. And when you do that, you need to have confidence in your predictions. So last few years, maybe 4 years or so back, I started bringing that to NETL to start looking at, can we use those techniques to predict the confidence in estimate the confidence in the predictions. So today I'm going to talk to you about that. So essentially my talk is, I'll tell you, why it's important, but if you make predictions with a computational model, how do you estimate your confidence? So my talk's based on that. I'm going to talk about 2 papers. These are my co-authors. Actually, on one of them I was a co-author, on the other I was not. Before I start my talk, I'll take a couple of slides to explain what is NETL. So you have an idea of our lab. So NETL is one of DOE's national labs. There are 17 of them. Our focus at NETL is on fossil fuels. So we look at coal, oil, natural gas. So how do you use that efficiently and in an environmentally friendly manner? That's our focus. And we at our lab, at other national labs, mainly the funding that comes to the lab stays there and it's entirely used for the research there. Whereas at NETL, most of the funding, 90% of it goes out because we do a lot of demonstrations at industrial scale. And say about 10% of that funding remains within in-house. And there is a research organization that's based on that funding. So that's there are these 3 research campuses. I'm coming from Morgantown, West Virginia. There's close by Pittsburgh, Pennsylvania, as well as Albany, Oregon. So these are the 3 research campuses. And this organization is called the Office of Research and Development. And we do research in various areas of interest to fossil energy. 2 main areas where we have a lot of work going on currently are in carbon capture and storage. So we have 2 large national initiatives to address issues with carbon capture and storage. One is the Carbon Capture and Carbon Capture Simulation Initiative, CCSI, and another is the National Risk Assessment Partnership. So the idea behind carbon capture and storage is this. We know that CO2 is a global greenhouse gas, so we need to control that. And the power plants, especially the power plants burning coal, are the main, maybe about the third of the CO2 comes from those plants. And these are point sources, and you want to capture CO2 and store it away so that it doesn't go into the atmosphere. At CCSI, we are looking at the capture process. How do you develop these processes fast? So that's our focus. And NRAP, they are looking at underground storage and the storage security. How do you want, once you store CO2 underground, you want it to stay there for a long time. So that's their focus. Okay, with that quick introduction, I want to talk a little bit about the motivation for this uncertainty quantification. So this example is from CCSI. So essentially, we are developing, if you use today's technology for carbon capture, the cost of electricity, the electricity that we get, it will go up by 60 to 80%. Because you're adding this carbon capture thing at the end of a power plant, so that adds to the cost, so the cost goes up. But we know that the energy that is used for separating is actually way too much. It's like 5 to 6 times the minimum energy that's required. So there is scope for decreasing that cost. So DOE focus is to decrease the, to keep the increase in cost of electricity below 35%. So we want to bring it down from 60 to 80 to below 35%. So what that means is you need new materials or new techniques to separate carbon capture. So what is shown here is some solvents that we are developing at our lab. This is a small pilot scale facility at our lab for testing these solvents. And this is a slightly larger scale device that is built by a company called ADAES. So they're developing a process for carbon capture. But all these developments are sort of at this stage. It's like a 1 kilowatt or so scale. And ADA is right now going to 1 megawatt. I think this year they will have a system that works at 1 megawatt. But what we really need, these power plants are 500 megawatts or more, 100 megawatts, 1 gigawatt. It's very large. So we need to go from this to this large scale. And as you go up in scale, the complexity goes up, the cost goes up. So we, and reliability is very important for the power plant industry. So they take steps. They take these small steps, go to 1 megawatt. I mean, these numbers doesn't mean anything. It's somewhat arbitrary, but you can imagine that they take multiple steps before they get to this large scale. So what we want to do is we want to use the power of computational tools to accelerate that. So we can do that. You can use computations to decrease the time between the steps, and perhaps also make those scale up larger. Okay, so these steps are chosen because they have a certain amount of confidence in going from one step to another. So it's like walking on snow. You're taking baby steps. But if it's dry, you can take larger steps, right? So that means you need greater confidence in your predictions of scaling. And that's where physics-based simulations can help. And for that to help, we need to quantify the confidence in our predictions. We cannot simply predict. So essentially what we are doing is, say if I'm going from 5 to 20, I only have data up to this point. I know all the things happened at smaller scales. Now I'm going to make this leap. So how confident am I in making that leap? So that's the question that I want to tackle in this presentation. So here's a quick intro to the model. So I call it physics-based because it's based on fundamental laws of physics, mass, momentum, energy balance. So this is, you can imagine the previous slide, one of the devices that you saw, those tall columns, they are called fluidized bed reactors. So this is a section of that. For some reason it stopped. Let's see. So this is a section of that fluidized bed reactor, and this is a movie made at NETL by my colleague Frank Schaefer. So you can notice that there is solids flowing. It's mainly flowing upwards, but you can see all these clusters coming down. So this is a fairly complex fluid dynamic problem. The way this model approaches that is by thinking of this as two fluids. So it's called a two-fluid model. Some people call it two-fluid model. And essentially it's similar to what you might be used to. There's the Navier-Stokes equations. It has a mass and momentum conservation. I'm not showing you the other conservation laws, but these are the two basics. And you need to do three different things to make it work. One is that there are these two phases. They're occupying the same volume. So you need to introduce a volume fraction to account for the fact that there are these two phases in the same place. These phases are going to exchange mass and momentum and energy. So you need to account for that. And the fact that we approximated these solids as a single fluid with an average velocity, you are throwing away all that information about the fluctuating velocity. So we need to keep track of that. So that's the granular energy equation. So that's a quick intro to the model. Actually, there's a much more model than what I have it in this slide. So the only things, you need to only remember two things from this. One is that it's a deterministic model, but with many parameters and many inputs. Secondly, it's a complex model. It takes a lot of time to solve it. It's not very easy to solve it. And if you substitute any other model, the rest of my talk would pretty much be the same. The details of this model doesn't matter. But this is the model that we are going to use for our uncertainty quantification development. So once we have the model, you all know that the first thing that you should do is to validate it. You want to make sure it's physically realistic. So here's a validation example where my colleagues have done a simulation of the pressure drop, that column. You look at the pressure drop at various levels and compare that at various heights. Compare that with experimental data. So all these diamonds are the experimental data. So I'll pause here for 2 seconds. Look at this figure and think, what comes to your mind quickly? I'll just take 1 second for you all to think. Well, you might think the agreement is good, especially because a CFD guy, you might think, yeah, that's a pretty good agreement. If you're an experimentalist, probably you'll say, not really. It's just average. And it's said that in the literature that John Grace is a famous experimentalist in fluidization. He and his colleague Tagipour, he's a CFD guy. So they wrote that usually if I look at all these papers written by modelers, they'll always say the agreement is good, whereas it's only fair. It doesn't agree well. So now my question is, does it matter, right? Well, how does it matter? How would it help if I said this is excellent? Or how would it help if I said it's only fair? So what should be the objective of validation? This is the current way we do the validation. And actually, there are answers, and my talk is essentially to answer this question. So the first answer is from ASME. So ASME in 2009 said that the objective should be to estimate what's called the delta model I'll explain that, what that is, within an uncertainty range. So, and they pictorially show what's going on here. So they'll say, okay, there is a reality of interest that you're modeling. So if you take the previous example, it will be the pressure drop at various heights. And you can experimentally measure that. So this isn't doing the validation, this is not prediction. So you're doing experiments and you're doing experiments as well as doing a validation simulation. But as you measure, there are errors that come into the picture. So those are the delta Ds. Here we assume that any known errors like bias and things like that are eliminated. So we are only talking about remaining things which are uncertain, and it's essentially as a distribution. Okay, so it's not a single value. And then we look at that reality and then we develop a simulation model. And models are approximate, right? You don't capture everything in the model. So right away we have made modeling assumptions, and that's delta model. Delta model is the uncertainty that you capture, uncertainty that came into picture because of your modeling. And as I said before, in a cost model, you have a number of inputs, so they all have uncertainties associated with them. So that's another source of uncertainty. These models need to be solved numerically, and that brings numerical uncertainties. And when you put all of them together, you get a simulation result. And the difference between them is the comparison error. And what ASME is, the standard is telling, is you need to have this delta model where you not only look at the comparison error, but you also look at the spread. Okay, comparison error is only a mean. If you got mean even 0, still doesn't mean that when you predict, your error will be 0, because there is a distribution, so you can fall out and could be incorrect. So that's the first part. But ASME did not talk about prediction. They only the ASME standard only talked about this the validation simulation. So essentially, what I want to talk about is prediction. How do you now take the next step? Okay. So before I do that, I thought I'll give you, a minute to read this. This is something a famous scientist said after a terrible accident. So my intention is for you to read the last sentence, but just wanted to check. Does anyone recognize this? Who said it and in what context? Mike?
When after the challenge disaster.
Exactly. So this is a very instructive quote, because they had this model that was not physics-based, that was used to develop confidence in how things work, and things could go terribly wrong if you don't look at the uncertainties. It's not that the model itself caused the accident, but you can be misled by fitting and then ignoring the uncertainties. All right, so let me move on. So that brings me to the main outline of the presentation. So essentially, I'm going to talk about these two papers. One is, you can think of this as sort of the engineer's approach. Okay, this is a paper that we published last year. And this one can be thought of as a statistician's approach. So this is my colleagues did this, and they submitted this for publication. It shows some different aspects of uncertainty quantification. So I'll start with the first one. So here, what we did was there was this paper published in 2011 by Roy and Overkamp. So they gave a framework for uncertainty quantification in a CFD model. And they demonstrated that with a very simple, simple compared to the previous model we saw. This was just 500 cells and a steady state, single fluid flow. It's very simple compared to a hydrodynamic model of a fluidized bed where you might need 500,000 cells. There's no steady state, things like that. So our purpose was to take their framework and apply that to the multiphase CFD problem. So I'm going to show you those steps. So it's it's sort of like a tutorial. So these are the 5 steps. So you do this for the validation simulation, and then you get the model form uncertainty, and then you can do that, use that in the predictive simulation and calculate the uncertainty. So that's the plan. So what do you have to do? You have to identify and characterize all sources of input uncertainty. So there might be a gas flow rate that you measure, but you never really, regardless of how many times you measure, it's always a distribution. It's not one value. So that's an uncertainty. But that's called a irreducible uncertainty or a aleatory uncertainty. Regardless of what you do, you're always going to have a distribution. There's another kind of uncertainty called epistemic, which is uncertainty coming into picture because of lack of knowledge. One example could be that in the fluidized bed model, there's a parameter called restitution coefficient, right? Say you didn't measure that, but you can still bound it because theoretical limits, it's 0 to 1. So that's a bound. So you have that much knowledge. But if you're careful about looking at the literature, you know that, this should fall between 0.8 and 1. So you can narrow it down. But still, it's not an exact measurement, still an interval. So those are epistemic uncertainties. Then you want to propagate that through the model, and I call that the simulator here. And I'll explain what's an emulator later on. And from this, you can estimate the model form uncertainty. And you also need to estimate the uncertainty due to numerical approximation. Once you have all these, then you can calculate the uncertainty in your prediction. So when you make predictions, you can also put a confidence band around it. Okay, so I'm going to go through those 5 steps. So in our example, we select, there are many input quantities, but this is, again, what I'm showing you is the methodology. This is not to say that this is not to predict the uncertainty in my model. This is just showing you how, given a model, how do you go through that, so that our interest was in developing the methodology, and so we made simplifications, to get things done faster. So out of the many inputs, we selected these 2, the mean solid circulation rate, so that the solids are circulating like that in this loop. So we used that as one of our inputs that we don't know. And then there is gas that is flowing through the system, so that we use the velocity of that as another input. And in uncertainty quantification, you also need to define what you want. Because the model can produce many different things, right? But but there are certain quantities that you're interested in. So in this case, we are interested in the pressure drop across the riser. So the pressure drop from here to there. So we said that's the quantity we are interested in. That's what we want to predict. So that's identifying and characterizing input uncertainties. Then we want to propagate the uncertainties through the model, and this requires many runs. So I said it earlier that the model is very expensive. So this requires like 100,000 simulations, and these simulations maybe take a week to do, so it's not physically possible to do that. So the way around is to create an emulator. You can think of that as a fitted surface, but then you need to consider the uncertainty in the emulator. So that's, in this case, we took that as the greatest error that we found comparing the emulator with the modeling results. And once you have built the emulator, you can, so this is the uncertainty in the velocity, so the velocity distribution. This is the solid circulation rate, and then you feed that into the emulator. Out comes the pressure drop, which is now not a single value, it's a distribution, and that can be shown as a PDF, or this is a CDF, the same thing. So essentially it's showing cumulative probability, right? So the input uncertainty suddenly now change a single value to a distribution. Okay, so that's what it has done. So Roy and Overkamp then defines. Okay, so this blue line is the input uncertainty, and then the uncertainty because of the emulator is the light blue. So the dark blue line is the CDF, and this is we consider the emulator as an interval, so that so this is the net uncertainty because of the emulator and the input, and these steps are the experimental data. You can see again experiments have uncertainty too, and Roy and Overkamp, they define this area, the minimum area between the prediction, the calculation, and the experiment as the model form uncertainty. So we calculate that as this quantity. Then we looked at numerical uncertainties. One is created by spatial discretization error. Again, you do grid refinement, and there is a what's called a mixed order analysis we can do for both time and spatial discretization. I won't go into all the details, but there is a recipe to convert that. So this is the pressure drop at a pseudo grid resolution, and you can convert that into a uncertainty due to numerics. Unfortunately, this turned out to be disappointingly large. Okay, so we are still not sure whether this is correct, or we need a better way to estimate this numerical uncertainty. But this is an illustration of the method, not really the calculation of a real predictive calculation. The second source of numerical uncertainty comes from time averaging. Okay, so this is a pressure drop as a function of time that we calculated, and what we need is actually an average pressure drop. But you can see, it fluctuates a lot. We can throw away some initial fluctuations, then it pretty much reaches a statistical steady state, and you can calculate an average pressure drop by time averaging over certain windows. So what this table is showing is my window size like 5, 10, 20, 40, and 60. And as you increase the window size, suddenly this becomes more and more accurate. But that means longer simulations, it's very complex. So we said 40, averaging over 40 seconds is a reasonable estimate. But that brings an uncertainty. Okay, so that's the uncertainty due to time averaging. Okay, now let's take a summary of all the uncertainties that we calculated. So for reference, this was the uncertainty in the experimental data. The input created like 1.6% emulator. Spatial discretization, as I said, that was unpleasantly large. Okay, so that points to maybe, of course, it says you need final grid, but also, is the technique that we use to calculate that correct? That's still a question mark, and we need to go back and revisit. But what this does is ultimately it gives us a model form uncertainty. Okay, this is from the validation simulation. So we have experimental data, so we can calculate this quantity. Now we are going to the unknown territory. Okay, we are going to scale it up and use this information to make predictions where there is no experimental data, and that's where we want the confidence bounds. We didn't actually do predictions, but I'm going to demonstrate to you what will happen if you do the prediction. So that's the next slide. So essentially, so this is the pressure drop as a function of cumulative probabilities, and this blue line, again, a single value, is normally what we do today is just calculate a single value, but that now has been converted into a CDF. So this is the uncertainty coming from the input. If you add the surrogate model or the emulator, that adds to this the uncertainty, and if you add the model form, that increases the uncertainty further. This is from discretization, this is from temporal averaging. So this, now you can ignore all the colors inside. Okay, This is called a P box, so this is this two S-shaped curves connected with this line and this line. Okay. That's the final output. So now, instead of a single value, we are saying this is the uncertainty in the total prediction. Okay, now you can ask, what good is this? How would I use this? So let's ask some questions to this. So this might be one question that a designer might ask is, what is the probability that the pressure drop does not exceed? I just arbitrarily picked this value for demonstration purposes. But there might be an economic reason or some sort of safety reason where they say, yeah, I want the pressure drop to be below this value, or I want it to be above this value. So what it does, this does is this P box then allows you to say, so you draw this line, and what it says, the P box says is this uncertainty is from 80% to 100%. Of course, 100 means it definitely is. So the worst answer is this. You have like 80% confidence that the pressure drop will be less than 24. So now compare that with what would have happened if I just had one value like 19 kilopascals and I give that to the designer saying that I predicted and the pressure drop is 19, right? So this is a different scenario. Here you can go back and interrogate this figure and figure out, well, I only have 80% confidence that the pressure drop will be less than or greater than this. And now the designer can decide whether to improve that or not. In some cases maybe 80% is good enough, but in some cases it may not be. Maybe you want greater than 90% or you want greater than 95%. So what that means is you might have to do better simulations, you might need more data for validation. So that's the beauty of doing it this way. You're not giving the designer one value and say, well, I'm confident. Okay, so this is showing the confidence in your prediction. So that's one approach. So by the time I got here, so I have time until what time? 4:30 or? Okay. I started thinking that, well, yeah, okay, now I can figure lots of things out of this figure, right? And so I said, well, what if I want to predict the confidence in that the pressure drop will be between, say, 14 kilopascals and 24? And can I say it's 80? And it's greater than 80? And I thought you can. And turns out you cannot. And I realized, my statistical intuition is incorrect. In fact, it's not an easy problem. I figured out that there are many different ways to do it, and there's no single answer. So it's, that is questionable. And so I was a little disappointed that, I don't even understand this basic statistics. But it turns out that people are not intuitive statisticians. Statistics, is something that we don't understand intuitively. And I was amused to read that in Daniel Kahneman's book, that he went and investigated, are people good intuitive statisticians? And he said, not even statisticians are intuitive statisticians. They can make mistakes. So the next few slides, I'm going to make it interactive. So you have to think of an answer that comes to your mind. I'll show you a series of questions. And what I want to do is, illustrate to you some characteristics of statistics and build that up to Bayesian calibration. That's my plan. Before I talk about the next paper. Okay. So here is a famous called Linda problem. This is what Kahneman came out with. And this goes like this. So Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with the issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. How many people think Linda is a bank teller? Raise the hands. Okay, only 3. How many people think Linda is a bank teller as well as is active in feminist movement? Okay, there's a lot more. All right, some people abstain from voting. I mean, there's no quiz, you're not graders, so you can, freely answer. So that's the statistic, and this is the majority of people that Kahneman interviewed. That's the answer most people got. That Linda is a bank teller and is active in feminist movement. But that is the wrong answer, because that's only the intersection of these two sets, right? So you can get fooled. So here what happens is some extra information actually confuses us. Okay, the next couple of examples I'll show you that you will not recognize some extra information in the questions. So here's the first one. So the Linda problem generated a lot of controversy, but this is pretty straightforward. I think if you have time, you can probably figure this out. So this goes like this. Mr. Smith is the father of two. One of his children is a boy. So let's assume that the probability is 1/2 to have a boy or a girl as a child. Okay? So for two boys, the probability will be 1/2 times 1/2, 1/4, right? But now you're given that one of his children is a boy. So what is the probability that both his children are boys? Okay, now that we know that one is a boy, is it half? Because it's like 50-50, right? Or it's not, it's 1/3. How many people think it's 1/3? Okay. How many people think it's half? All right, a lot more people thought. It turns out it's 1/3, and it's pretty straightforward. You can easily prove that. But my point was mainly this. See this. This is an alternative scenario. Here I'm telling you that we meet him walking along the street with a young boy whom he proudly introduces as his son. So it looks pretty similar to me to the last one, right? Two children, one is a boy. What is the probability that both his children are boys? So I said the previous one answer was 1/3, right? How many people think it's 1/3? Okay, few. How many people think it's half? Okay. You could have guessed, in this case, half is the correct answer. Does it make you wonder? It seemed pretty similar, right? But actually there was a hidden information that you missed. It is that Mr. Smith had a choice to pick one child or the other to take to walk. And if you don't really fully follow it, you can just do a paper and pencil, just say boy, girl, boy, boy, and see, how many he could have selected, and you see that, yeah, that's indeed, it's 50%. So there's information that, was there which you did not recognize. And here's another famous example. Some of you might have seen this already. Okay, this is the Monty Hall problem. Okay, so there are people in their hands. Has everyone seen this? Okay, all right, I'll just explain this anyway. So this is a 70s TV show. You go to the show, there are 3 doors, and you are supposed to pick one door. Behind one door is a brand new car, and behind the other 2 doors, there are goats. And the typical player is playing for the car, not the goats. So, let's say you picked door number 1, and Monty will, open door number 3, and he'll say, do you want to pick door number 2 now? So the question is, would you pick? Actually, this was written out in the American Statistician, the magazine of the statisticians, and it's generated a lot of controversy. People were fighting that, this is not true, what you're saying is incorrect. And then Marilyn Wassermont, in her Parade magazine, there's a column that comes. She presented that, and she got a lot of angry letters saying that you're completely wrong, what are you saying? Things like that. So the question is this. Okay, starting out, your chance was 1/3, right? 3 doors, 1 has a car, so 1 out of 3. So Monty, having opened one door and revealed a goat, the Does it still remain 1/3? Probably not. That's, doesn't make sense. But would it be half, if you switch? Because now there are two doors. One has a car, one has a goat. Would it still be half? Or would it magically become 2/3? How many people think it would become 2/3? Okay. Some of you actually already saw this. In fact, that's correct. It becomes 2/3, and the reason is, Monty knows where the car is, so that has a bearing on the answer. So let me move on to another one. I'm pretty close to getting to the Bayesian calibration. So this is, again, if you know this, it will be very obvious, but if you don't know, this could confuse you. So this is 80% of women with breast cancer will get positive mammographies. A 40-year-old woman had a positive mammography in a routine screening. How many people think, what is the chance that she actually has breast cancer? Okay, nobody thinks. So you all know this very well. And you're right. You cannot infer that from this data, right? It needs, so that's the probability, this is the information that I just presented, but we need two additional pieces of information. Now we need to know what is the probability of prevalence in the population, as well as it's very important to know false positives. You could test positive, but when you don't have cancer. And there is Thomas Bayes, almost 300 years ago, he came up with this formula. Essentially, given this information, you can now calculate what is the probability, in this case, of having cancer. And this is a famous formula, but again, it is very controversial. I think a lot of statisticians didn't like it, and even famous statisticians like Fisher said, this is nonsense. And this supposedly went through, it was very popular, then it decreased in popularity, went again, and then again went back. And apparently now it is popular again, and it's used for a lot of calibrations. So it's the same formula. So what we do is we have information that we know before we do a certain experiment. And given that experiment, we want to figure out what's called a posterior PDF. So that is, what is the value of the parameters after we have an observation. So this technique is now widely used for calibration, and that's the second part of my presentation is on this Bayesian calibration technique that my colleagues used. Okay. So here, again, the same CFD model I showed in a previous slide was used, but this is for a different fluidized bed system. This is called a bubbling fluidized bed. The one you saw previously was called a circulating fluidized bed. It's the same equations, but you solve it with different conditions, you get different regimes. And they stuck in a lot of heat transfer tubes, and they were measuring the bubble free. You can see these bubbles. These are actually simulation results, although they look pretty close to experimental values. And they're measuring the frequency of the bubbles around these tubes as a function of the angular position. In this case, my colleagues, they selected as inputs this gas velocity coming from the distributor and the angular location around the tube as another input parameter. And they used a bunch of modeling parameters. I will not go into all the details, but I want to point out that these are all continuous variables, restitution coefficients and packed bed void fraction, etc. But what I want to point out is they also used a categorical variable, drag model. So you used 3 different drag models. So it's not a variable, right? It's a categorical. You can use drag model A, B, or C, and they're using Bayesian calibration also to determine which one is the best one of 3. as output. Again, as I said earlier, in all uncertainty quantification studies, we have to define what's the output that we're interested in. Okay? A complex model has lots of things coming out of it, but in this case, they looked at bubble frequency and bubble phase fraction. So in an actual engineering problem, there might be things that the designer wants, right? The velocity profile is something maybe the CFD analyst is interested in, but the designer, all he cares about is maybe a conversion in the reactor or a pressure drop or things like that. But so we need to define that. So they define bubble frequency and bubble phase fraction as the quantities of interest. So let's say, so this in 2000, the Kennedy, O'Hagan, and Higdon, all these guys, they came up with a methodology for what they call expensive computer model calibration. So if you have a simple model, you don't really need all this, but like MFIX or CFD model, it's very complex. It takes a long time to solve it. How do you calibrate that? So they represent it. So again, essentially the idea is this. You have a certain prior knowledge. So these are model parameters, and they're all, say, n parameters with a probability distribution function. And if you're absolutely sure, then you can think of that as a delta function, but usually it is not. So there is a uncertainty. And there is something called a discrepancy function. Okay, so this is similar to the model form uncertainty I talked about earlier, which was a sort of a simple thing, but the statisticians use a more complex function. I think I will have an example to kind of explain what it is later on. So given this prior knowledge, and say you have new evidence, so you have experiments, which you can use to infer the goodness of your model or the validity of your model, how do you come up with this, what are called the posterior distributions? So starting from, say, theta1, this distribution, you want to get the correct distribution based on this evidence. Similarly, theta n, all the deltas, you can calibrate all of them using this technique. So this, essentially the prior knowledge and the inputs, they go into the simulator, it produces the output. So this is like, you run the CFD model, you get the bubble frequency as an output, and then you can use the calibration framework and come up with this posterior distribution. And once you have these posterior distributions, you can use your simulator to do the predictive simulation. So that is where you don't have any experimental data. You're going beyond the scale. And you're going from, say, data up to 5 megawatt to 25 megawatt, where you don't have any experiments at all. And you want to predict, and you want to bound the uncertainty. This also allows one to do what's called a sensitivity analysis. So that is, say, suppose I find, I have certain uncertainty in my predictions. Can I backtrack and see which one of these guys are important? Which one should I measure more accurately? Is it the restitution coefficient that's most important? And it is good to know, right? Because then instead of measuring 100 different things very accurately, I can focus on that one thing which mattered a lot. Okay? So you have that ability to, in this framework, to go back and interrogate and figure out what is more important. That's called a sensitivity analysis. So you can imagine that this might go through some sort of loop, and finally you'll come up with a really good set of posterior distributions, and then you do your prediction. Okay, that's the scheme. And so they did this calibration. And here are the results for various parameters. In here, the blue lines in all these graphs are the prior distribution. Okay, this is what was known before considering any of the experimental data. So this is given before you do the calibration. And these stair-step, the black stair-step, that's the posterior distribution calculated by the calibration framework. So these are the posterior distribution. So if you look at all these, there is actually not a whole lot of difference between the prior and the posterior. They're pretty close, right? But there are two places where it made a difference. So in the case of friction angle, particle-particle friction angle, they started out with sort of a uniform distribution of the friction angle between these two values. And the calibration said it should be the 25 degrees is the correct friction angle given the experimental data. Likewise, the categorical models, they looked at these three drag models, and this predicted, or the calibration gave us an answer when a new drag model is the most preferable, given that experimental data. So, that's pretty neat. You not only calibrate your continuous variables, you can also get information on categorical variables. So that's those are the results that they obtained. And here are the discrepancy functions. So here we had two output quantities of interest: bubble frequency, bubble phase fraction, and we had two input quantities, velocities and the angular location. And at the intersection of each, there is a discrepancy function. Okay, and what they are, you can think of them as a family of functions. Okay, and that's what being shown here. There are a number of realizations of that function, and these red bands give the 95% confidence bands. So each one of these discrepancy functions. So what came out of this BSS and our analysis is posterior distribution of all the parameters and these discrepancy functions. Now that we have this information, which was obtained with validated external data, we can go ahead and make predictions. So that's what's shown in this slide. So they did this calibration for lower velocities, and they use the calibrated parameters and the discrepancy function for predicting what will happen at a higher velocity. So I'm just showing one example. You're looking at the bubble frequency as a function of angular location on the tube. So if you simply make predictions with just the calibrated parameters, this is what you get as the mean, the blue line, the solid blue line, and the broken blue lines are the 95% bands. So now we want to add the discrepancy function. So that's given by the solid red line and the broken red lines. So this is our final prediction. So it's not just a mean, but it's a mean plus this confidence band. And you can get any confidence band you want. This is just shown, 95% is shown for an illustration. We can, if you want it for 10%, it's possible to plot that. Okay, now let's see, how well we did. This is, of course, it's just a simple example, but you can see fairly that, these experimental data actually falls well within this confidence. And that's what we want. So we want to predict something unknown, predict the uncertainty bounds, and then be able to say, what is the confidence bands we have around that. All right, so that concludes my talk. So this is the summary slide. I just want to quickly recap what we looked at. So again, this is in relation to multiphase CFD, and in other areas, this status might be different, but at least in multiphase CFD, the current practice is to do the comparison error. We do the calculation, look at the experimental data, come up with a comparison error, and then we come up with a qualitative assessment. The model is good, the model is excellent, the model is fair, whatever. That's a qualitative assessment. And the ASME VNV standard, it says that you not only come up with a comparison error, but you also have that distribution around it, because just the comparison error is not enough. And if the comparison error is 0, you could still be off when you do predictions, because there is a distribution. So that's what the ASME standard asks you to do. What we did in our work, this is the first paper I talked about. So we calculated what's called the P box. You remember the two S-shaped curves with the two lines. And what that gives is the total uncertainty at the prediction point. Okay, so you do the validation, get the model form uncertainty, and then you can have the prediction point, you can have the p-box. And what Kurt Storlie and others did was they calibrated the model parameters. You notice that we didn't do that, right? In our paper, you only got the model form uncertainty. So they calibrated the model parameters as well as calculated a discrepancy function, which is sort of like a model form uncertainty. And what enables them to do then is to do the total uncertainty at the prediction point with optimal model parameters. So yeah, I left, you're right, it's a Feynman quote. It's, again, remind you that if you want to take predictions to the point where we can reduce the number of experiments. So ideally what we want to do is we want to do experiments of small scales, which is controlled, which is cheap, which are fast, and reduce the number of large scale trials. Okay, that's what we want to do. And to do that effectively, I think computational science can help, and to get that help, you need to have confidence, or you need to know the uncertainties in your predictions. And thank you for your attention and your questions.